So we're going to start with a very basic lesson today. We're just going to cover these few slides, and then I'm going to show you a video that summarizes basically the point of this slideshow. This is legit the beginning of what? This is the beginning of physics. Just so you know, every single thing we've done so far, none of it was what? Physics. That was just what? The mathematical description of what? Of movement or motion, exactly. Absolutely no physics was there. Actually, it was more of a math than physics, right? Because we solved equations, we sketched graphs, we analyzed, trends and so on. Now we talk about the why and the how and so on. Okay? All right. So, constant and definition. So, what's the first thing you have here? So, a force is best. Okay, when you use a force, you do what to? Yes. So, when you use a force to anything, you can either do one of two things. Either you what? Or push. There's absolutely no if the force can actually cause what? If it can cause what? Motion or displacement. Okay, I could push on this. I did exert a force, but this is way too massive and way too bolted to actually what to actually move. But in general, a force either pushes or pulls. Okay, 100%. There you go. So that's the effect. How do you know there's a force? If you let go, something else happens. Yes. So either a push or a pull. Okay. So because it's either a push or a pull, it must have a what? It must have a what? Pull or push must have a what? A direction, which means effectively, force must be considered a what? A vector. There you go. But now you know that oftentimes we could think of vectors as what? As what? We could think of vectors as scalars, only if we play with what? With the directions and plus, minus, and that kind of stuff. Okay? So therefore, force is a vector quantity. But again, we'll get around that, just like we now said, oh, velocity, you can think of it as speed as long as you know the plus minus directions and so on. Okay? So force is a vector quantity. Okay. All right. So let's go next slide. Okay. So can you guess what's the physical symbol of force? What's the first one that comes to mind? F. Uppercase or lowercase? How many people say lowercase? How many people say uppercase? Okay. So the vote is in. It's actually uppercase. So the question now is, what do you think we use lowercase for? Okay. Again, by the way, lowercase f in physics is used almost exclusively for a very important quantity. I'll give you a hint. Nope. Thank you. What? Frequency. How frequent is an event? Frequency in physics is what? Lowercase f. Uppercase f is reserved in any physics you take. I don't care which, like grade 11, grade 12, first year. You will always see that's what? It's a capital F with a what? With technically an arrow on top, because it must be associated with a direction somewhere. Okay. All right. So you have to give me a direction if I ask for the force as a vector. What if I ask just for the magnitude of force? Then you only have to give me just what? Just the magnitude, and that's it, just the number. Perfect. Yes. And by the way, oftentimes I will only ask for the magnitude, even in grade 11 and grade 12. Okay. Physical symbol is just an. Okay. All right. Okay. So everyone, today's lesson is just talking about what? Just talking about forces. Okay. And this is gonna be like so we're gonna talk about two kinds of forces. There are two types of forces. Number one, sorry. This one is called the what? The fundamental forces. Go ahead. Fundamental forces. Here's the good news about the fundamental forces, everyone. The only time we're going to talk about it is just today, and you will never hear about it until the end, even of what? Of grade 12, even first year. Why? Fundamental forces are the forces actually dealt with if you become a what? A professional physicist. So basically, all these Nobel Prizes that are given every year, which actually one was given just last week in physics and chemistry and all of these other fields, the only way you can actually really go deep into studying fundamental forces is only if you major in what? In physics, astrophysics, astronomy, some types of engineering, not all of them. So for example, civil engineers never study what? Fundamental forces. Chemical engineers, maybe. Mechanical, never. Electrical, yes. So again, depending on the what? On the engineering. Chemistry, yes, because chemistry deals with the very what? With the very tiny and the very small. The currency of chemistry is what? Electrons. And electrons actually subscribe to the what? To the fundamental forces. How many fundamental forces are there? 4, no more. That's it. It's been agreed on. Every physicist out there agrees there are only 4 fundamental forces. Okay? Why are they called fundamental? Because they are the reason why everything No matter how small or how big, happens the way it does. Okay? All right. They only study those in advanced physics. Okay. So, for example, I guess Behat said that he's eyeing astrophysics or astronomy. I guess yes, he will take courses. If you actually go to these fields, like I did, you will take courses called quantum physics, quantum mechanics, particle physics, nuclear physics. Basically, you study the fundamental forces on the very, very, very microscopic scale. Okay. The other one we care about, by the way, it doesn't have a set name. I like to call it what? Engineering forces. Why do I like to call it engineering forces? Because they are the forces that engineers, or basically specialists in building and operating things, actually deal with. Okay? So engineering forces, how many are there? You know what? It depends on how complex your system gets. Okay? We will study a few of them in grade 11. I think in grade 11 we're only going to cover 5 engineering forces. In grade 12 we're going to add 2 or 3 more, and in first year we'll add 1 or 2 more, and that will be most of it for the whole thing. Okay, so that's why I say it's a multitude. Why? I depends on the problem. By the way, one problem could have only what? One what? Engineering force. One problem could have what? 2, 3, 4, 5, depending on how complex it gets. Okay, the maximum I'm going to give you in a problem in grade 11 is a problem with what? 4 engineering forces only. What's up? You know what? In my career, I don't think I've heard more than like 9 or 10 tops. Okay, you define more as you what? As the system gets what? More complex and more elaborate to be analyzed. Okay, I call them engineering forces because they are the forces that engineers care about when designing and building things, from buildings to nuclear reactors to microchips, all of that. Okay. Okay. So today we're just gonna talk about what? Tomorrow we'll talk about what? And we will start actually what? Applying some of them, but in a light way. Okay? All right. So everyone, let's go to the first slide. Okay. How long have people actually believed or proposed that there are 4 fundamental forces? I would say for a century so far, like since the 1930s. In a way, since what? Since the names like Boltzmann, Bohr. How many people have heard of Bohr? Niels Bohr. Where do you hear about Bohr? In chemistry. Bohr Rutherford diagram, even though both of them were what? Were actual professional atomic, not nuclear, atomic physicists. Okay? So it was the 1930s where basically what? All of the foundations for the new wave of what physics have been what laid out. Einstein, Heisenberg, Schrodinger, all of that stuff. This happened in the 1930s. So, what is the first fundamental force? Gravitational. By the way, I do not put them in order of importance. All of them are extremely important, okay? But I will put them in the order that we're going to cover them. So the first one is the gravitational force. By the way, very important to call it what? Gravitational, not what? Not gravity. They're not the same. They're related, but they're not the same, okay? Number two. Number two is more known. It's called the what? Electromagnetic force. Electromagnetic force. The last two have weird names, but that basically shows you that physicists, even advanced genius physicists, run out of names at some point. The first one is actually called, and this is the official name for it, the strong nuclear force. So what do you think the fourth one would be? Yes, you're absolutely right. If there's a strong one, they actually came up with the other name, which would be the complete opposite of it, which would be the weak nuclear force. So let's talk about the first one, gravitational force. Okay. Gravitational force. What is the easiest way to define gravitational force? It is the what? No, what's the word underlined? Underlined. What's the first word underlined? Attractive. Everyone, gravitational force is never what's the opposite of attraction? Repulsion. Gravitation is never a repulsive force. Gravity or gravitation never pushes things away. It always pushes them what? Closer together, inward, never outward. This is one of the first important features of gravitational force. Gravitation is one of the forces that actually what makes object move closer and closer all the time. Okay? Now, what is the only attribute or property of an object to be under gravitational force? It just has to have one thing. Can you tell me what's the only particle in the universe that has no mass? Nope, it has a mass. The mass of the electron is 9.11. times 10 to the negative 31 kilograms. Unbelievably small and light, but yet it does have a mass. So if you have a very sensitive scale and you manage to put an electron on it, it would read what? 9.11 times 10 to the negative 31 in kilograms. So technically it has a mass. No, even quarks have a mass. By the way, how many people have heard of quarks before? Quarks are basically the particles inside of what? Protons and neutrons. So yeah, no, they have mass too. There's only one particle in the universe that actually has purely zero mass. Second, photon. Photon is the particle of what? Light. Light is the only particle, or the photon is the only particle with what? Zero, absolute, not even zero like relative, zero exact. It's a Exactly. That's why gravitational force does not what? Classical gravitational force does not affect them absolutely anyway, because they do not interact as if they have how much? 0 kilogram mass to them. They are a pure fireball of energy. A photon is a pure energy, has zero mass to it. Okay? So the only thing that needs to be there for an object to be under gravitational force or to experience it is to have a mass. How big of a mass? Doesn't matter. Gravitational force acts on galaxies as much as it acts on what? Electrons. Obviously, we do know that the gravitational force on galaxies is much, much, much more massive and much heavier, or much bigger, I should say, in magnitude than the force on two electrons, maybe around the hydrogen atom, but it's still there. It just happens to be almost very close to zero in the case of an electron. Okay? So in other words, it exists between two galaxies, which are very heavy. By the way, everyone, listen up. Get used to heavy is not the same as what? Heavy is not the same as big. And light is not the same as what? You could have something heavy, but what? Small. And you could have something light, but what? Big. Like what, for example? A cotton ball. A cotton ball is very what? Very light, but very what? Very huge in volume. How about the opposite case? What? So what? Okay, what can be very heavy yet very, very small in size? A steel ball, exactly, like the ball bearings. Very heavy. You can actually feel the weight of it, but it's very what? Very small. Or what? What is the densest? What does density mean? Dense, if something is very dense, what does that mean? Very what? Very heavy, but very small. What is the heaviest, the dense, something that's very, very dense in the universe? It's actually in space. A what? A black hole. A black hole is a what? Is a star. That star getting what? Collapse on itself, which means what? It keeps the same mass, but what happens to the radius? It's getting what? So is there less packing or more packing? More, until the gravitation of it gets so strong, even light could not escape. That's why they call them a what? A black hole. You cannot see it, but you can see the effect of what? Spiraling objects around it. That's how they actually detect them in stars. Yep. All right. Everyone, one important thing about the gravitational force. It's the what? It's the weakest. How weak is it? Okay, I'll tell you how weak it is. I remember one of my amazing profs in Western. Okay, he passed away, but he taught me particle physics. He used to say, like when he taught us this stuff, he used to say, that was back in 2005. And in 2005, he was diagnosed with cancer and he was going chemotherapy. So obviously, chemotherapy makes you very what? Very, very, very weak. Okay, and he used to say that I think he was like 60 something at that time, and he used to say, "I'm 60, whatever, and I'm going through chemotherapy." And yet, look, he would hold a chalk or something. He would hold a chalk like this, and he would say, "Even with me being super, super weak and frail, I am stopping the entire Earth from what? From pulling it down." Do you see what I mean? By the way, is the Earth light or heavy? By the way, what's the mass of the Earth? I know. By the way, this will become a very common number because we're going to use it a lot in this year. The mass of the Earth, everyone, is 5.98. Yes. What does that mean in standard notation? 598 and 22 zeros, because you're going to hop how many times already? You already hopped 2, so how much is left? 22. It's 598 with 22 zeros in what? In kilograms. Okay? When something is very, very massive, it has a huge what? It has, and yet he would say what? I am stopping the Earth from what? From pulling it down just by exerting how much of a force? A very, very small force. And yet he is canceling out gravity. Do you see what I mean? So even the Earth, with its mighty mass, Cannot do anything. Once I let go, what happens? Yeah, once I let go, it falls. But I could just cancel it just with a very small amount of force. Okay? So that's the first proof. What's the second proof that gravity is the what? Is the weakest? They just discovered, experimentally the what? The proof that Einstein predicted that gravitational force actually existed. So he predicted it theoretically on paper back in 1920. He published a paper and he got ridiculed for it because he's claiming something that people are like, no way, this doesn't happen. But he said, but the math proves it, which means what? One day, what's going to prove it? Physics. They just discovered the very first proof that Einstein predicted that the gravitational force actually exists just 5 years ago. Why did it take such a long time? Because the gravitational force is very what? Weak. What does that mean? Exactly. You need something that basically is so precise, so sensitive. Okay? So it doesn't care about any properties except for what? Mass. So tell me other properties of objects other than mass. Density. It kind of cares about density because it factors in what? Remember, density depends on two things: mass and size or volume. So technically, if you say density, it's kind of like an inaccurate answer because density is still what factors in mass. What other properties does not care about mass? Again, well, could be volume. Okay, sure. Yeah. What else? Volume is size. Volume, 3D volume is size. Huh? Shape, yes. Color, electric charge. Anything else doesn't matter. It just matters what? How much what? How much mass it has. Okay, that's all we need to know about what? Gravitational force. All right. What was the second one? Second one on the list? Electromagnetic. Thank you. Okay. What was one of the important features of gravitational? The very first one we said. Gravitational is the what force? Attractive force. How about electromagnetic? Because we know opposites what? Opposites attract. And likes what? Likes repel. Exactly. What we hear from what? We learn from grade 10 science. So electromagnetic could be attractive or repulsive. Okay? So what does the electromagnetic force depend on? Well, by the way, electromagnetic is really how many words? What are they? Electricity and magnetism. Okay? It was the first two forces ever that were unified, in one. So what does the electromagnetic force require to actually happen or to actually be felt? Well, it requires the object to either have what? Electric charges or magnetic what? No, magnetic. Yeah, by the way, there is no such thing as a magnetic charge, just so you know. There is no such thing as a magnetic charge. There is an electric charge. There is an electric charge, which could be positive or negative. There is no magnetic charge. There are magnetic properties. Like what, for example? When you have a magnet, how many poles does a magnet have? Two poles, a north pole and a what? And a south pole. So in a way, it's got like a what? A positive charge and a negative charge. Basically, you need two opposites to attract and two likes to repel. Okay? All right. Again, this one doesn't care about the mass. It just cares about how many or how much electric charge it has or how much magnetism it's got inside of it. Okay? Here's the thing. Gravity was the weakest. Sorry, gravitation, I should say. I'm going to focus on gravitation. All good? Thank you. Gravitation was the weakest. This one is the what? This one is the strongest. How strong is it? Well, okay. First of all, it is the basis of chemistry. Why is this the basis of chemistry? What happens in chemistry, everyone? When a chemical reaction happens, what really happens? What's the currency of exchange between molecules and compounds? Electrons. What drives an electron to hop or to change environment from, for example, let's say when you, why? Because basically the electron is what? Is feeling more what? Electromagnetic attraction from one environment to the what? To the other, so it gets stripped out. Like for example, how many people have covered ionic bonds and covalent bonds? By the way, what's the difference between ionic and covalent? Ionic is a full what? Is a full migration. How about covalent? Sharing. But even when they share, are the electrons right in the middle? Never. Why? Because there's electronegativity. Which one is more electronegative, oxygen or carbon in CO2? Oxide, which means what? The electrons are going to be more towards the what? More stolen towards the. Thank you. Exactly. So that's my point. The chemistry depends on what? Depends on what force? Electromagnetic force. By the way, do the electron migration depend on gravitation? It could, but in a very what? Very minute, weak way. By the way, what's holding you together right now? You might say, oh, well, you just taught us that gravity holds everything together. But is gravity strong enough to hold you together? No. If gravity was the only force in the universe, you would not exist right now. Because gravity is not strong enough to what? To pull you together and keep you stable. What is strong enough to keep you stable? Electromagnetic force. What's keeping you stable right now is all of the what? All of the attraction between what? The different what? The different protons and electrons swimming through your body. Gravity would not be able to do that. It's way too weak. Okay? Okay? But does that make sense? Electromagnetic is the real strong what? Strong person in this relation. Okay. So we're done how many so far? Two forces. What's the next force? Strong what? Nuclear force. Okay. So the question is, why is it called strong and why is it called nuclear? Well, let's see. So strong nuclear force. Can someone tell me what are the two particles that could only exist inside of the nucleus? It is the attractive force that tightly binds the only particles that could exist in the what? In the nucleus, which are only two. It's the binding force of neutrons and protons. It's the binding force of neutrons and protons. Okay? Let me ask you a question though, everyone. What's the charge of a neutron? What's the charge of a neutron? It's neutral. That's where the name came from. They actually found out that it could go through an electric charge without what? Without swaying left or right. It just keeps going what? Because it has absolutely no, it's not affected by any electromagnetic force. How about the protons? They are p protons positive. My question to you is, okay, let's take an example. Carbon. Does anyone know the atomic number of carbon? By the way, there's a difference between an atomic number and atomic mass. Does anyone know the difference? It's important to know it. Atomic number of an element, atomic mass or weight. Okay, hold on. Raise your hand. Who would like to do it? Okay, Mohammed. Define to me what's the atomic number of any element. Aha, number of what? Number of protons inside of the what? By the way, can you also say it's the number of electrons outside of the nucleus? But there's something you have to watch out for. Number of electrons could what? Could change because electrons are what? Very easy to what? Remove or add. How easy is it to change the number of protons? Because of the what? Because of the strong nuclear force. Do you see what I mean? So here's my point now. So protons. So what's the atomic number for carbon? The basis of life. 6. So what does that mean? C6, right? C, and you put I believe 6 here. What's the number here? Does anyone know the atomic mass? What does 12 mean? It's got 6 protons and 6 what? And 6 neutrons. Exactly. So what does that mean? We have to have a total of how many here? 12. 6 of them are what? And 6 of them are neutrons. Okay, so let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I need to remove this one. Okay, but they're very what? By the way, is carbon unstable or stable? No, it better be stable. If it's not stable, you would be radioactive right now. You are made of what? We are made of what? All organic material is made of what? Our carbon-based life form, right? Imagine if carbon was unstable. What would happen to you daily or yearly or every decade? You would decay. What does decay mean? You yourself would be decaying into other elements and giving out what? Gamma radiation. Is that happening right now? No, it's not. Which means carbon is very what? Uranium is very heavy, which means what? Which means the nucleus itself needs to lose weight. Like it's too what? Unstable for its own weight. So what happens? It degrades down to what? The atomic table, right? Like it goes down to what? To thorium, to cobalt, and so on. By giving out what? Alpha particles, beta particles, and what? And gamma rays. Making sense? But carbon, thank heavens, is what? Very what? Very stable. By the way, there is what? There is one. How many people know the word isotope? What's an isotope of an element? It's the same what? Same? Okay, does anyone know the most famous isotope of carbon? Carbon 14. Why did they call it carbon 14? Because it's got what? So is it now lighter, same weight, or heavier than normal proton, no, normal carbon? Which means technically, is it less or more radioactive? And that's why they never say what carbon 12 dating. They all say what carbon 14 dating. Carbon 4. By the way, in your body right now, there is a very small amount of what? Of carbon 14, which is how they what? Date bones in your body. Is it making sense? Carbon 12 would never decay. Or if it's decay, it takes millions of years. The half-life of carbon 14, how many people know of something called half-life? We're going to talk about a lot when we talk about energy. The half-life of carbon 14 is, so does it decay quickly or does it take long? But at least it's what? It decays. That's the point, okay? So the question now is, half of these, well, let's go back to this. Half of these are what? So I'm going to say positive, 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 positive. Are you with me so far? Is it natural for positive charges to be very, very, very close to each other? What did we say about electromagnetic force? Opposites attract, but likes what? So theoretically, just by considering the electromagnetic force, what should happen to those bunch of positives? Should they stay together or should they fly apart? And yet, that's not what? Thank you. That's not happening. The only reason they proposed, what does propose mean? Suggest. They suggested the existence of what? Is because this violated what? What does this violate? So they were like, there has to be what? Hold on. So what did they say? They said there had to be another what? Another what? That is strong enough to prevent the what? To prevent the prying off, or the basically the what? The repulsion, to prevent the flying apart. So they called it what? They actually called it strong because it's actually what? Stronger than what? Than the electromagnetic force. They also called it what? Nuclear. Why? Because it only exists in the nucleus. Here's what they actually found. This is strong enough to what? To hold them what? Together. But they actually found out that if the protons are far away more than the usual distance of a nuclear diameter, like whatever nano or picometers, the strong force completely what? Completely disappears. And what comes into effect now? Electromagnetic force, because they are what's known as free particles. Do you see what I mean? So only if they are in close proximity, they are what? The strong force is the what? Is the governor. If they are further away, more than a couple of hydrogen atom nuclei diameter, which one is the governor? The electromagnetic. They become regular charges like Isaac Newton, whatever dealt with, and so on. Is it making sense? So that's why they call it strong nuclear. Strong because it's strong, and nuclear because it only exists in the what? In the actual space of a nuclear. It has no effect outside of the nucleus. So here's the question: how strong is it really? How strong is it really? Ladies and gentlemen, this is how strong the what? The nuclear strong nuclear force is. It is so strong. Listen up. If you can actually what? If you can break them apart, the amount of energy released, the amount of energy contained in them released. Ladies and gentlemen, yes, Hiroshima and Nagasaki. Those are the two what? Those are the two atomic bombs released on what? Hiroshima. Hiroshima was the small one. It was called Little Boy. Little Boy, dropped in August 6th. Nagasaki was the more destructive one. 3 days after. It was called Fat Man. Okay? All right. Why do they call it weak? Okay. They call it weak. No. Everyone. They call it weak because, first of all, within the nucleus, it's what? It's weaker than the what? Than the strong force. Okay? What does it do? What does this force do? It is actually the force that causes the super fast processes in the nucleus known as nuclear transformation. What are nuclear transformations? Well, Baha, you said there are the small particles inside the protons and neutrons are called what? Starts with Q. Quarks. Everyone, quarks are particles that could actually what? Shapeshift. What does shapeshift mean? Yeah, change shape or change identity. Okay. Quarks come in six kinds. Okay. And the names for them, I am not kidding you. These are the names of the quarks. There's up and down, there's top and bottom, and there's charm and strange. They just called it because of the what? They just needed opposite sounding names, like calling north and south, black and white, positive and negative, and so on. Okay? When two quarks change, when one of them changes into the other, a proton could change into what? Or a neutron could change into what? Tell me a question, everyone. If a proton here changes into a neutron, how many protons do you have now? You went from 6 to what? 5. From 6 to 5, which means, but how many neutrons do you have now? 6 to 7. Technically, you're still at what? You're still at 12, but are you at the same element now? Thank you. That's why you never define an element by its atomic mass. You define by its atomic what? Number. You never define it by the whole thing. You define it by the protons inside of that number. And that's why. Okay, what would have happened, everyone? What would it be if it was the other way around? What if a neutron turned into a proton? Instead of 6 and 6, you'd go what? 5 and 7. But which one would be the 5 now? And which will be the 7? What's got 7 protons in its nucleus? Nitrogen. Because remember, it's what? It's carbon with 6, nitrogen with 7, oxygen with 8, right? Fluorine with 9, and 10. You get to the what? The last one, which is the noble gases, which is neon. Make sense? Yep. All right. Okay. Go ahead, everyone. This is what I just told you. It breaks apart the inside of neutrons and protons and turns them into each other. It is the weakest inside of the nucleus. It also has no effect outside. So always remember, the strong force and the weak force only exist where? Inside of the what? They completely do not exist outside of, like, what's the diameter of the hydrogen atom, which is the smallest atom? Everyone, the diameter of the hydrogen atom roughly is 1 picometer. So a hydrogen atom from one side to one side is about 1 picometer. What's a pico? It's 10 to the negative 12. So it's not a milli, not a micro, not a nano, 1,000 times smaller. This is roughly the size of the what? Of which atom? What? The hydrogen. By the way, hydrogen is the what? Is the what? Is the smallest one. Why? Because it has an atomic number of what? By the way, what's hydrogen? It's 1 proton. That's it. It doesn't even have any neutrons. By the way, what if it has another neutron? It's still hydrogen, but it's a what of hydrogen? An isotope. It's called what? It's called 1,1. How about if it has two neutrons? It's still a what? It's another heavier isotope. It causes what? Yeah, everyone. It causes nuclear decay in all of its forms. Alpha decay, beta decay, and gamma decay. We're going to talk about decay so much for a whole day when we do energy transformation.